Alrighty, let's see. So this is gonna be Physics 1940, University Physics 2. We're gonna be talking about electromagnetics. It's gonna be chapter 29, our Holiday and Resnick book. So we're gonna define magnetic force and magnetic forces exert or magnetic fields. Magnetic fields exert force on a moving charge. Now, this moving charge, which is your current, can create a magnetic field. And as we've seen from the previous chapter, so we have a straight wire. This straight wire, we have the magnetic fields. This is going out, and this is going in. Actually, let me get a different color on these. So here's your out. This is going in the screen. This is out of the screen. Which means, according to your right-hand rule, your current is going to be going in that direction, where your magnetic field is going to be going this way. And we define the magnetic field, beta, as mu naught I over 2 pi r. Mu naught, let me get a different color. This is your probability in free space. So free space. And this is going to equal to 4 pi times 10 to the negative 7. I think I don't have to just write this down better. 4 pi times 10 to this Tesla meter per amp. Now, our 2 pi r that we have over here This is going to be your circumference of the circle, which is your circles right over here. Let me actually make this a little bigger, better so you can see it better. Now, so our magnetic field, and I'm going to write it down real fast, 2 pi mu naught I over 2 pi r. Now, the force that exerted is going to equal to Q times V cross beta. Now, and let me go ahead and write down the side over here the rule for the cross product, which is in this case would be A cross B is going to be your absolute value for A, absolute value for B, cosine sine the angle between them. So we have a cross product between V and B, and in this case, it would be your Q V B sine theta, which is going to equal to, which we can take your magnetic field and substitute it on here, so you get QV times mu naught I over 2 pi r sine theta. So that's our force. Now, the closer you get to the wire, the stronger the magnetic field. And vice versa. The further you go out, the weaker the magnetic field. So for example, let's say our current in this case would be 2 amps and our radius is 3 meters. That means our magnetic field in this case will be mu naught I over your 2 pi r. And in this case, it'd be 4 pi times 10 negative 7 times 2 for your 2 amp divided by your 2 pi times your 3. In this case, the 2 cancels out, pi's cancel out. So you should get mu naught over 3 pi. And if we calculate that, we should get 1.3 times 10 negative 7 Teslas. Wonderful. So again, our force is going to be equal to QV cross beta. And again, Q is the charge, V is the velocity, and the voltage, and B, that's your magnetic field. In this case, so your Q, that's your charge. Let me go ahead and label these. Your V, that's your velocity. And then your B, that's your magnetic field. Now, this little fella is called your Lorentz equation. And basically states that the force and magnetic field exerts on the charge Q moving with velocity V is given by F equals QV cross beta. So we're going to take this little fella that we have, F equals QV cross beta, which is, according to the rule that we solved a little while ago, is going to be QVB sine theta, which we saw that is going to be QV times mu naught I over 2 pi R sine theta. Now, when we have same thing, IL cross beta, it'd be IL beta sine theta. So let's say in this case we have two wires. So here's our first wire. There's our second wire over here. So we got our first wire going out, in, out, in, out, in, out, in. Same thing with this one. Let's say we get this is your out, 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 and then going in, 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 in. We got the current I1 and your current I2. And let this separate by distance R. Now, and let's say the length of the wire, let's say the length is L2, this is L2, so this would be the length of L1. Now, the net magnetic force on I2 caused by I1. So you want to find the force going in from, let's say, F2 to 1. Go ahead and this one. Means that F2 to 1 is going to equal to IL I2 L2 cross beta 1, which is going to equal to I2 L beta 1 sine theta. And if you plug it in, you should get I2 L mu naught I1 over 2 pi R. Again, that comes in out into our force. Oh, I forgot to write the force on this one, which is your ILB sine theta. That brings us down to Ampere's law, which is for any current geometry that produces a magnetic field but does not change in time. So let's see, you have your wire over here, and then here's your magnetic field. You got your current going in on top. I. You're looking at this cross-sectional area, where that's your delta L. It's going in that distance over here, from here to here, which is going to be basically your circumference, which is your 2 pi R. And this is your beta. Now, with Lenz's law, it states that your summation of your magnetic field, delta L, is going to equal to mu naught I, which basically means that if you take your beta to be summation of your delta L is going to equal to mu naught I, which means that your beta is going to equal to mu naught I over your delta L, or your summation of all your places that it's affected. And this is going to equal to mu naught I over your 2 pi R. So basically, you're into your closed integration of your beta dot d of s, and I'm just gonna say, or I'm just gonna say d of l because I've been using l, so I'm just gonna say d of l is gonna equal to mu naught I, the current for the enclosed, and so this is gonna equal to your closed integration beta dot dl, which is your closed integration of beta cosine theta d of s cosine theta, which is going to assume is going to go to 1. This is going to equal beta enclosed integration for what we have for d of s, which is going to beta times your d of s. Again, we said that as the circumference is going to be 2 pi r, which means that your magnetic field times your 2 pi r is going to equal to mu naught I, which means that your beta is going to equal to mu naught I over your 2 pi r. And this is going to be outside your straight wire. Now, let's say we got a long straight wire. Let's say we got this wire over here. we take a little section of it and we want to see the strength of the magnetic field and the current of a carrying wire. So let's say we're looking at this one over here, which I'm gonna call this same thing, D of L, which is that's the area we're actually looking at. And let's say we have a point B. This point is going in with something called R hat. Here's your point B over here. Uh, this is creating a theta angle where, let me get a different color. It's perpendicular to it. There is the I, D of L, which is the L again, is the area that we're going in on. So R hat is the unit vector that points from D of L to our point B. Now current length will be I, D of L, produces a differential magnetic field d beta at point P. The magnitude of the field d beta produced at point B at a distance R by a current length IDL is going to be and here's your equation. dB is going to equal to mu naught over 4 pi I d of s sine, or d of s, d of L. Sine theta divided by r squared. This is a pi. So we got a distance r, and I'm just going to call this is the distance that we're actually going in. From here to here, that's your distance r. So let me go ahead and write this down. R is the distance from d of s, d of L to our point P. This magnetic field distribution, which is your mu naught over your 2 pi over your 4 pi, is going to equal to mu naught over 4 pi I d of L cross R, which is your unit vector divided by R squared. And again, according to our rule, if you solve it, it's going to be mu naught over your 4 pi I, the first one, which is going to be IDL, times the second one. Now, the second one is going to be your R hat, which is going to be your unit vector. Unit vector is going to be 1. So it's going to go up to 1. So this is going to be sine square theta, sine square over R squared. And that's what we call, and this is a little fella, that's what we call your Biot Savart law, which is two French scientists that actually developed this law. And again, I'm going to write this down. This is going to be used to calculate the strength of the magnetic field in a current carrying wire. So basically, we just developed the Biot Savart law, which again is stated as dB equals mu naught of 4 pi IDL cross R hat divided by R squared. And again, R hat, this little fella, let me go ahead and write this down, is a unit vector, which is going to equal to 1 for our example, which is going to equal to mu naught I dl sine theta over 4 pi R squared. Now, the direction of d of s cross R is going to be into the screen. Now, to find the magnitude of the magnetic field at point B, we multiply the integration by 2. This is because the magnetic field produced in the upper half and bottom half of the wire at the set are the same. Let me go ahead and draw my wire. This is my wire over here. Let's say I got a point P over here. And I'm just going to go like this. This is going to be your R hat. And I'm going to call the distance over here just to make it different than little r, I'm just going to call big R so we won't be confused. This is creating again your angle theta. And your d of L. And I'm just going to call this distance big L because you're distributing over L. So this means that your magnetic field is going to equal to 2 times your integration from 0 to infinity of your dB, which is going to equal mu naught I over your 2 pi. Again, you get the integration from 0 to infinity. And we said it's going to be sine theta d of s over r squared. Now, we have, according to Pythagorean's theorem, our r, or r hat, is going to equal to your square root of it'd be your a squared plus b squared equals c squared, which is going to be your L squared plus your r squared. Which means that our sine the angle is going to equal to your big R over your small r. In this case, it'd be big R divided by your square root of L squared plus r squared. Well, we can take our little sine all right, so this sine theta that we have, and let me get a different color actually. Here it is. So here's your sine theta. So here's our sine theta. So we can go ahead and plug it in. Let me go ahead and do that. So this means that our magnetic field, which is your mu naught I over your 2 pi, integration from 0 to infinity, r dl over L squared plus r squared to the 1/2 times L squared plus r squared. And this is going to equal to mu naught I over 2 pi for your integration from r dl over S squared plus r squared, or square L squared. Do the 3 over 2 when you add 1/2 plus 1. And which means that the magnetic field is going to equal to mu naught I over 2 pi r times S over, and keep calling S, L, we called it L, over S squared plus do the 1/2 from 0 to infinity, and this is going to equal to mu naught I over your 2 pi r. So your magnetic field is going to equal to mu naught I over your 2 pi R. Now, I need to go ahead and go through this. Why do we use electromagnetics? Why electromagnetics? Well, which we give it the letter EM. When you increase current, that means you increase the strength. Because again, you can alternate that. When you switch of I, your magnetic the magnetic field turns off. If you reverse I, reverse the poles. Also, when you increase the current, that means you increase the magnetic strength, magnetic field strength, which basically you control the magnetic, basically, field. And that should conclude chapter 29 for Holiday and Resnick book.